Welcome to Biochemistry 412, a hands-on approach to the biochem you learned in 410 and 411. This class is typically only offered in the fall and summer 2 semesters. I'm your instructor for the class, Dr. Ayers. My administrative assistant for your absences is Mrs. Rausch. Both our emails are there. The Canvas website has contact information for the teaching assistants and everyone else. Office hours are posted on the website. When we do them by Zoom, there'll be one link for all people. You can come to anyone's office hours or make an appointment. In this class, we'll teach you the theory and principles of electrophoresis, chromatography, lots and lots of biochemical assays, biochemical calculations, because there is a lot of math in biochemistry, how to analyze and interpret experimental data. We'll go over the use of a lot of common lab equipment and how to keep a lab notebook. For this class, you need a physical copy of the lab manual from the MSC bookstore, typically only $15 or $16. The lab manual will also be posted online in sections by class periods, but you still need the physical copy. You'll need a bound composition notebook for your lab notebook. Grades, lectures, etc. will be posted on the Canvas website, including schedule and everything. Note that all quizzes and exams are on the computer with lockdown browser. Bring your laptop, though we have a few computers available in the lab. General grade breakdown, 30% worksheets. You'll have 2 attempts at each of the worksheets because it's to help you understand the material. Quizzes are 240 points. That's after dropping the lowest grade. So if you miss a lab, you're okay because you get to drop that quiz. For the final exam, it's 40% of your final grade. And the lab performance is worth 60 points out of 1,000. We'll talk more about these. Any discrepancies must be reported within a week or we won't fix them. For your lab performance grade, note that much of the work is done in pairs, but both partners should participate fully. If your partner does all the work, you'll be graded accordingly. Not to mention on the final exam, there's a practical portion. So if you're letting your partner do all the calculations, the pipetting, the spectrophotometry, etc., you probably won't do that well on the final. If you're a safety hazard, ignore lab rules, etc., we can take a penalty here. Note that when you submit work, it should all be in your own words. You cannot share a graph with your partner. You need to make that graph independently, or you will get half credit. A lab notebook is the record of what you did and why. It should be clear enough to repeat in 5 years. Sometimes the experiments are very complex and you need notes. If you don't have a good notebook, you may not be able to repeat your experiments, or someone coming after you may not be able to, or if you get someone's notebook and get told to repeat the experiment. Sometimes it can be important for legal things such as patents, and they might even have a witness sign and date notebooks daily. For this class, you need an inexpensive composition notebook with lines starting the next class period. Simple one like you had in 5th grade with a marbled cover works. Puppy dog, sparkles, whatever you'd like on it. Note that the quizzes and final exam will be open notebook. Quizzes will be held at the beginning of most classes to make sure that you've prepared. These will include pre-lab questions, things we're doing that day, steps of the procedures, what's involved. Also, questions from previous labs to make sure you keep your knowledge base up. For the notebook, put your contact information. Note that you do get to use it on the final exam. I've had one student lose his, and he was dumpster diving trying to find it because he thought the library had taken it out with the trash. You get to use it on the final exam. Write legibly in ink It's important in science not to hide data. So your notebook is designed that if you rip pages out, we can tell. Also, you can't erase. You must simply draw an X through it. Before coming to class, read the manual and fill out, handwritten in ink, the date of your experiment, purpose, 1 or 2 sentences with the overall reason for doing the experiment. Today, I'm making a cell-free extract from bacteria containing GFP and RFP TAT. Background, 1 or 2 paragraphs on what you're doing and why. What are you going to do with a cell-free extract? What is GFP? What is RFP TAT? That kind of information. Next, you should have your procedure in enough detail to repeat it without the lab manual. This kind of information will be tested on quizzes. The lab manual is written in great gory detail. You do not need that much information. Part of doing the handwritten part is it will make you think about what's important, distill the information down to what you need. During class and after class, you'll add your results and data analysis, raw data, tables, calculations, etc. Please note that the worksheets have many of your calculations. If you can calculate specificity constant on your own, terrific. Most of us would probably like to have the steps in our lab notebooks though, because you will be asked to calculate it. You are allowed to glue in the graphs that you make in Excel and gel pictures. However, the rest, it's to help you understand and memorize it better. Sometimes there are no real results. You'll simply put how you labeled your tubes. Discuss what your data means. Discuss any problems. If you have these absorbance values of GFP and RFP TAT, does that mean you successfully purified it? If not, discuss any issues that you had. Write a conclusion supported by the data. I successfully purified GFP and RFP TAT, or maybe you didn't. In the lab, we have workstations for each pair of people. In the small drawer in front of each student, there are safety glasses for the times when we need them. In the larger partner drawer between them, labeled with your workstation, you have a bunch of stuff that you can see in the picture, even Sharpies. Note that that workstation is a good number to have on your samples. You'll be sharing heat blocks and centrifuges and storing samples in the freezer. And it's much better to have your workstation number on it than to have your initials or nothing at all. The contents of the drawer are color-coded as much as possible. So this drawer, there's yellow tubes, yellow racks, sometimes white because we don't always have yellow. The bench that these would be at would be the yellow bench. There's yellow tape. The top tape on the pipettes are yellow, so we know where everything goes. And when we find them laying around, we can put them back. In the drawer between partners, there are cuvettes to use, also extra tubes and tips when you run out. All right, let's go over some of the safety rules for the lab. Note that these are in the lab manual, and they'll be posted on the board and in slides. There's no eating, drinking, chewing gum in the lab. You must have closed-toed shoes and your hair tied back. We will provide you with eye protection and gloves when we need it. If there's an emergency, dial 911. Fire extinguisher up front by the door. First aid kit, the same by the door. All I really have are Band-Aids because I can't even carry aspirin because it might expire. There are emergency stop buttons, big red buttons by both of the doors. If you need to turn off all electricity and gas, that's the button to push. In the sink in the lab, there's an eye wash that we will demonstrate in class. There's also more eye washes in the hall and showers if you need them. A spill kit up front, though paper towels are usually sufficient. I have a broken glass container by the fume hood in the lab. For glass only, please, but let us know if something breaks. Your backpacks and purses should be either slung under the bench or on the hook under there. It's your choice. They need to be out of the path if there's a fire so that people can get out quickly. Material safety data sheets are on the door or on the computers. And there's a safety agreement in the lab manual. If you take one out now and sign it and pass it to the back, please. In the lab, we have 3 different types of waste containers, depending on what we're doing. There's regular trash that you put in the trash cans around the classroom. There's also a small bag on the bench that's in an orange holder. Those bags are mostly for regular trash until we tell you differently. You empty them into the bigger trash can. Glass trash, again, by the fume hood. Don't put your cuvettes in there because I get in trouble if you do, and I don't like getting in trouble. The biohazard container will set out when we're working with bacteria and DNA, and then you'll put all your trash in there so it can be autoclaved to dispose of it. At that point, you'll be using the small bags on the bench for biohazard trash and emptying the contents into the appropriate trash. Keep the small plastic bag, though. We try to reuse them to save on plastic. Before you leave class each day, put everything away. Don't leave your tips on the bench and pipettes around. Clean all your dishes as necessary. Rinse them with distilled water. Put them on the dish card up front. Empty your trash bags on the bench, keeping the bag again. Clean your bench and let us know if anything is missing. All right, let's talk about working on your skills. Some of you are in research labs and think you're really good at pipetting. Some of you are, but some of you aren't. And some of you are totally new to this. You want to make sure that both you and your partner can pipette well because it'll help you get out quickly. There's a section in the lab manual for how to pipette with our micropipetters. You'll be working on worksheet 1 for this one. We'll also be doing spectrophotometry using red dye 40. Your lab notebook will start next time, as will our experiments, and the worksheets are due according to the schedule, both in your lab manual and on the website. We have 8 great specs in the lab. They have a 6-cell holder that holds 1 blank. We always use a blank in this class, and 5 samples that can be read at once. The light beam travels from left to right to left. It doesn't matter how you orient the cuvettes, with a 1 centimeter path length. So you want to put them in this orientation. There is also on the cuvette an arrow that you can match up with the arrow on the spec to know that you're in the right orientation. If you put it in the wrong orientation, it'll be less than 1 centimeter and it will not read accurately, so your values will be off. The cuvettes get placed so the light goes the long way from left to right to left. The next one goes there counterclockwise and so on, so that they rotate into the proper position in the front when they are read. Today, you're going to construct a standard curve using Excel. We'll give you plenty of practice with Excel if you're not experienced at it. You're going to use solutions of a solution of known concentration so that you can calculate the concentration of an unknown solution. First, you need to determine the extinction coefficient for red 40. This is simply the proportionality constant that lets you figure out the concentration of a solution. And then you're going to figure out the concentration in a sample of unknown concentration of red 40. For your graph, you want to make sure you add a title, axes, units. Almost always we'll use scatter plot with the points not connected. Add a trend line, equation, and r². Most of the time, the trend line should pass through or close to 0. Otherwise, you're often not pipetting well. Sometimes we'll go ahead and force this through 0 to account for low concentrations of reagents. Title of your graph is often considered the hardest thing. I tend to think it. Think about what type of graph you're making. If you're making a standard curve, then it's probably a pretty straightforward graph, often concentration that's increasing, something like that. But if you tell me Lineweaver-Burke plot, I know I am concerned with the assay type. There'll be a substrate, a product, an enzyme converting that substrate into product. You want to tell me what's being measured in the spec on your graph. I know for Lineweaver-Burke, I expect a positive y-intercept, a negative x-intercept. I care about Km and Vmax. A lot of information there from the words Lineweaver-Burke. For your graph today, you're going to measure a series of dilutions that should increase linearly in absorbance with increasing concentration. If you have any outliers, you need to redo them. On this graph, you can see the data points are not connected. There's simply a trend line added. The equation, y equals 0.01x plus 0.002. So this has not been forced through zero, but you can see it goes really close to zero, and you could go ahead and force it through zero. R squared of 0.998. I expect most of you will get R squareds today of 0.998 or higher. It means the closer to 1, the better your data fits your point, your graph. What happens then if you get a value that's significantly higher than you would expect on your line? What could have gone wrong? Well, one of the first things you should check is, have you mixed it well? In this class, you should mix everything. The samples before you take them, the samples in your cuvette, always mix well. It makes your experiments go better. This is a nice, easy fix because the student could go back and mix it well, put it back in the spec, and it'll probably then fall onto the line where it should. What happens if you have a point significantly lower than expected? This also can be an easy fix. Chances are you have it in the wrong orientation in the spec. Simply flipping it into the correct orientation will also make it go on the line. It is, of course, possible that you haven't made your reactions correctly and you need to remake them. Some days in class, you'll be doing reactions where you do 10-minute incubations, cooling on ice, adding other components. Pay attention to all of this before you have to go start over. I will have you stay in class till the very end, until you get good data. But if you get good data earlier and we approve of it, then you can leave early. All right, here is a graph where everything is wrong. If you look at the title, you're simply restating the axes. Does not help the reader at all. On our x-axis, we have alcohol concentration, but we don't know the alcohol. We don't know the units for the concentration. The y-axis, what are the units of absorbance? Is it nanometers? No. The wavelength is set to a certain number of nanometers that does not change. Absorbance itself has no units, although it looks like you're saying nanometers here. The series boxes on the right can just be deleted. We will do a couple of graphs or a graph with 2 data sets on the same graph. And then you would want this for this kind of simple graph. It does not help you at all. And looking at the data, they connected the data points and then added a trend line, which makes it really difficult to see. Note too that their trend line is significantly above zero. That means that they're not pipetting that well. They have, however, included the 0 point on the graph, which is good. Sometimes students forget that their blank is the 0 point and should be graphed. Could this graph be the effect of drinking margaritas on a college student? Alcohol concentration increases, the absorbance increases as it does. Here's a better version of the graph. We now know that we're looking at the conversion of ethanol, a substrate, to acetaldehyde, a product, using the enzyme alcohol dehydrogenase. The data points are not connected. The trend line is nice and clean throughout. Equation, there's no B value because it's forced through zero. It still has an R squared, goodness of fit of data, of 0.9989, so that's really good. The x-axis, we now know it's alcohol. The alcohol is ethanol, and the units are millimolar. Y-axis, we're following the absorbance of NADH. at the specific wavelength of 340 nanometers. There are no units here. In this particular case, we cannot directly follow ethanol or acetaldehyde, so we have a linked reaction where we're measuring production of NADH 1-to-1 with your acetaldehyde. Taking a look at Beer's law, what's your extinction coefficient on this graph? Well, it's simply the slope of the line, so in this case, 0.0123. Well, what are the units? Let's figure that out. For Beer's law, absorbance has no units, so the epsilon CL has to cancel out any units to make none. Our path length is 1 centimeter, always in this class. Concentration, today it's millimolar. It could be milligram per mil or any other unit. So to cancel out those units, our extinction coefficient would have to be units of millimolar -1, centimeter -1. In this case, your actual extinction coefficient would be 0.0123 0.0123 millimolar -1, centimeter -1. All right, the last slide. Safety today. There are no particular safety requirements. Red 40 is simply food coloring. It can go down the sink. Cuvettes go into the regular trash. Gloves and eye protection are optional.